All right, good afternoon. Welcome to a test review for the Unit 4 end of unit assessment for the Illustrative Mathematics Unit 4, Grade 8. And we are going to just go through about 7 problems and talk about solutions and talk about answers to those problems. And let's get started. All right, so we have a problem here, and this one here is an equation that 2 people have solved. The equation here is 2/5 of b plus 1 equals -11. My solution is b equals -25, and Tyler's solution is b equals -28. And here's the work. Do we agree? So let's take a look at the work and see if we can spot any mistakes or errors that have been made. And it looks like we got my here, 2/5 of b plus 1 equals -11, and the next step is 2/5 b equals -10. So she's done something with this positive 1. It looks to me like she has subtracted it. Subtract 1 here and subtract 1 here. Okay. So if she's done that, then what should we get? So if we have -11, excuse me, minus 1, do we get -10? No, we actually get -12. So here is the mistake that she has made. This number here is supposed to be -12. So if that's the case, then if she did -12 times 5/2, she actually will get the correct answer. So my solution is not correct because this answer here does not make sense. -12 should be the answer here, not -10. Okay, so let's look at Tyler's work. Let's see what Tyler did. So it looks to me like Tyler started with the same equation, and then his next line is 2b plus 1 equals -55. So this says to me that Tyler did some multiplication. He multiplied, looks like multiplied by 5 here. So he multiplied this by 5, and then he multiplied this by 5, right? So, but when you multiply by 5, you have to multiply everything in the equation by 5. All the terms need to be multiplied by 5. So 2/5 of b times 5 is 2b. -11 times 5 is -55, but 1 times 5 is not 1, it's 5. So that means that Tyler's answer here, he needs to have a 5 here instead of a 1, right? So he's got to multiply that by 5 as well. That would change his answer here because then he'd be subtracting 5 instead of subtracting 1, and then dividing by 2. So he would have arrived at the correct answer of -30. Another option for these kinds of questions always is, yeah, you can analyze the work they did and see if you can spot mistakes in the work that they did, but you also have the option of just doing the work yourself and solving the equation yourself. So yeah, you can subtract 1 from both sides and then multiply both sides by 5/2, just like mine did, and then you would end up with a solution of -30 if you do it correct. And the same thing with Tyler. Okay, so that's number 1. Now with number 2, we're going to have a few equations that we need to solve and show the work for. So I'm going to type these out, and we'll go over the steps, and you can certainly pause and process as needed. So the first equation is -3w minus 4 equals w plus 3. So the first thing we would do is we would say, all right, well, are there any terms we can multiply out, multiply out, or distribute, or combine? So in this case, no, because we both have a w and a constant term in both sides. So what I work with my students is we work on balancing. When we have variables on both sides, we want to put all our variables on one side, and we do that through what's called a balancing operation. And the way we do a balancing operation is we take the coefficient. I always work with the students to tell them to move the lower coefficient, but in reality, you can move either coefficient. You can move either the -3w or the w. Whatever you choose to do, though, you're going to move all of your w's to one side. And I always go with the lower one because then I get a positive amount of w's. So I'm going to add 3w to both sides, and that's going to give me -4 on the left. Remember, we keep that in subtraction and make it a negative, right? And then w plus 3w is 4w plus 3. Then the next step I'm going to do is I'm going to subtract 3 from both sides. So by subtracting 3 on both sides, I am going to be moving all of my numbers to the other side and have nothing but w's on the right. So then what do we get here? So when we do that, we have -7 equals 4w. And then if I divide both sides by 4, after that, that would give me w equals negative. Positive is negative, so -7/4. Or if you like decimals, -1.75. So that takes care of that equation. Our next equation is 3 times 3 minus, 3 minus 3x equals 2 times x plus 3 minus 30. So with this equation, we're going to want to do some distribution first. So the left side, when we distribute that, 3 times 3 is 9. And then 3 times -3x is, 3 times 3x is 9x, and then we're going to subtract them. So 9 minus 9x. And then on the right side here, 2 times x is 2x. 2 times 3 is 6, and then we have this minus 30 on the outside. And then we're going to simplify that now. And one little rule here is if we have more than 2 terms on one side of an equation, a linear equation like the ones we're doing in this video, you're going to have something to combine unless you have multiple variables involved, in which case maybe you will have 3 terms on one side. But generally speaking, if you've got more than 2 terms and you're trying to solve an equation, there's going to be something that you need to combine. So in this case, it's the plus 6 and the negative 30. So we'll leave the left side alone. That's all set. 2x and then plus 6 minus 30, or negative 30 plus 6, whatever you want to say, is going to be minus 24. Okay, now it's time to collect. Our negative 9x is the lower of the 2 coefficients. So we're going to move that to the other side by adding 9x to this side and adding 9x to this side. So that's going to give us, let's see, we'll have 9 on the left, and that will equal 2x plus 9x is 11x minus 24. Then we're going to subtract 24 from both sides. And when I do that, sorry, I said subtract, I apologize. I'm going to add 24 to both sides. So I'm going to just write plus 24 here. Don't mind the no color change. Understand we're adding 24 to both sides. So 9 plus 24 is 33. That equals 11x. And then I'm going to divide 11 on both sides. That's going to be x equals, or 3 equals x. And I can just switch it around and say x equals 3. Excuse me. Okay, the last equation we have here is 1/3 of z plus 4 minus 6 equals 2/3 of 5 minus z. So before I write this, I'm just going to go ahead and do a fraction clearing of this, because we've got a denominator of 3 here and a denominator of 3 here. I'm going to multiply both sides of the equation by 3, and that is going to take care of my denominator. So let's type out while we do that. When I have the first term, which is 1/3 of z plus 4, that's all one term. Remember, parentheses, we don't separate terms, right? The parentheses themselves are sort of a part of the term. So 1/3 of z plus 4, if I do that times 3, that's just going to be 1. So it's going to be 1 times z plus 4. I'll keep the 1 there just to illustrate that 3 times 1/3 equals 1. And we're going to be subtracting, well, 3 times 6 is 18. Remember, when we multiply both sides of an equation by a number, we have to multiply every term by that number. So 6 is its own term. That has to be multiplied by 3 to become 18, in this case minus 18. Then it equals, okay, so 2/3 times 3, that's 2. And remember, when we multiply a denominator and a multiplier of a whole number, these two things cancel and we're left with just what's in the numerator. So 2 times, and then the same deal here, 5 minus z, because that's still part of the same term. All right, so we did the clearing of the fractions. Now let's distribute. Well, 1 times that is just z plus 4, so we don't have to worry about that. Minus 18 equals 2 times 5 is 10, minus 2 times z is 2z. And then on the left side, we also have an additional combination, the 4 and the negative 18. That's going to be z minus 14 equals 10 minus 2z. Okay, so for balancing here, we're going to add 2z to both sides, because the negative 2z is the lower of the 2 coefficients. So we're going to have 3z minus 14 equals 10. And then we're going to add 14, to both sides. That's going to be 3z equals 24. And then divide by 3 on both sides, z would equal 8, not 89. 8. Okay, so there's our solutions to these 3. And of course, for purposes of our video, understand that, yeah, you should take these numbers and you should be checking these answers. You should be plugging 3 into this equation and make sure it works. You should be plugging 8 into this equation and making sure it works. Okay, let's go to the next page. And we're going to decide whether these are true for all 1 or no values of x. So here's a tip for this kind of question. When you're trying to determine how many solutions an equation has, a dead giveaway is if you can spot the same amount of x terms on one side as the other. So because we have 6x over here and we have 6x over here, this is going to cause this equation to drop the x's completely, and you would just be left with negative 4 equals negative 4. Well, if we end up with a true statement, that means that there are infinite solutions. Okay? So one little trick for you is that when you catch that you've got the exact same amount of x's on one side of an equation, all you really need to do is look at the numbers. Okay? And if there's distribution that has to happen, distribute it. Get it so it's in its simplest form before you make the determination to make sure you have the amount of x's on the same side and that you end up with the same number, because if in the case of number 2, where you have a 4x over here and a 4x over here, these are going to cancel, but you're going to be left with negative 6 equals 3, which obviously is not true. So if it's not true, that means that there are no solutions. Okay? So remember, these are called in math class, we call these identities and contradictions. Okay? If you end up with an identity, that means that you have infinite solutions. If you end up with a contradiction, you end up with no solutions. But with the third one here, because we have negative 2x here and we have negative 3x here, and there's no further simplification that you can do, that means that you're going to have a unique solution for this one here when you simplify it out. So in this case, this will be one solution. We don't have to solve this particular question, but just for future reference, the solution is actually x equals 0, if you're curious. Okay, now, next problem. here we have a problem we can approach a couple of different ways. We actually, let's first read the problem and kind of understand what's going on, and then we'll sketch up something and then see what we can do. So Diego's got 11 bucks and begins saving $5 each week, and he is saving $5 each week towards buying a new phone. At the same time, Diego begins saving. Lynn has $60 and is spending $2 per week on supplies for her art class. Is there a week where they have the same amount of money? How much do they have at that time? Okay, so this is actually like a systems problem where we can write two equations and we can actually get an answer that way. We could take that approach and certainly do that. Before we do that though, let's just make sure we understand what's going on. So with Diego, if I kind of make a table of what's going on here and say that here's the weeks and here's the money, right? I'm just drawing with my mouse, so don't worry about that. And here's the money that's involved. If he's at like the start, which means the week 0, okay, how much money does he have? In this case, he's got $11 to start off. Because it says he's had $11 and then he begins saving, okay? Now, after the first week, how much money does he have? Well, if he's adding $5 each week, he's going to add $5 to that and have $11. At the second week, he's going to have $21, okay? And maybe do one more. Third week, he's going to have $26. So we kind of have an idea of what's going on with Diego. We actually have enough information we can create an equation to kind of make this make more sense. And just to make sure, just to be consistent, let's do Lynn, all right? And with Lynn, same format, weeks and dollars. With Lynn, at the start of her counting of her money, she's got $60. But then as she is spending now $2 per week, so after the first week, she's going to be down to $58. After the second week, she's going to be down to $56. After the third week, she's going to be down to $54, and so on. So here's the information we can make equations out of this, right? You'll notice that the right side is changing by 5 every single time. That x changes by 1. So that means that the rate of change is 5. So y equals 5x is an equation that we can use to model this increase. But further, because she starts, or Diego starts with $11, that's a he gets plus 11. So if we kind of think of Diego's money as however many weeks he's been saving times 5 plus 11. And then since we're using equations, let's let x equal the weeks, and y is the money. All right, now over here, same deal. This time we're actually going down by 2 for every week. So the slope or the rate of change here is negative 2x, negative 2 for the rate of change, and then negative 2x for the linear equation. And what is her starting amount? $60. Okay, so there's nothing wrong at all with extending this table and seeing where we can find a week that's exactly the same in both of them. But we also have the power of algebra to get what we need to do here. So if we know that we're looking for when this equation here is equal to this equation here, they both are equal to y, right? They're both equal to money. So we want to know when the money is the same. So we can actually make an equation out of these two expressions. 5x plus 11 equals negative 2x plus 60. Because we'd be interested in seeing at what x value does 5x plus 11 be the same as negative 2x plus 60. So if I solve this equation really quick, let's add 2x to both sides. Let's make that, and then let's subtract 11 to both sides, and then we'll divide by 7. X would equal 7. So that means at the seventh week, Diego and Lynn will have the exact same amount of money. They also want to know how much. How much do they have at that time? So at the 7th week, Diego's got 5 times 7 plus 11. So Diego's got $46, okay? Because we'd be subbing in that x of 7 plus 11, and then that y would equal 49. If I do it with Lynn's equation, I should get the same thing. Let's make sure y equals negative 2 times 7 plus 60, and then that's going to be y equals negative 14 plus 60, 60, which means y equals 46. Did I say 49? I meant 46. I'm sorry, over here, 46. Sorry about that. Thanks for catching it. If you were screaming at your screen in the next 5 minutes, give the video a like for me saying, predicting that that's what you were doing. All right, so 46, you get the same thing for both. You get the same x value works, and you get the same y value for both, so it concludes that your answer is correct. And again, if this equation thing doesn't jive with you, there's nothing wrong with extending this table. Go to the 4th week, go to the 5th week, go to the 6th week. When you get to the 7th week here, and when you get to the 7th week here, you should have 7, 46 for both of your values. All right, so for this one, this particular question, we have a graph that goes with this. So we have zucchini on the x-axis and broccoli on the y-axis, and both of those quantities are in pounds. So let's talk about what we got here. Andre is in charge of cooking broccoli and zucchini for a large group. He has to spend all $17 he has and can carry 10 pounds of veggies. Zucchini is $1.50 a pound, and broccoli is $2 a pound. One graph shows the combinations of zucchini and broccoli that weigh 10 pounds, and the other shows combinations of zucchini and broccoli that cost $17. Name one combination of veggies that weighs 10 pounds but does not cost $17. Well, if we understand that 10 pounds is the maximum, that means that the amount of broccoli and the amount of zucchini need to add up to 10, okay? So just to kind of, I know this is something you just want to put down there just so you can understand what's going on. If X is my zucchini and Y is my broccoli, that means that the sum of these two values always has to be 10. So if I have 10 pounds of zucchini, I cannot have any pounds of broccoli. So if you look over here and see this point right here, that actually is the value that I just described right here. So let me fatten that up a little bit here. How about there? Okay, that's a little better. That point right there, that's 10 pounds of zucchini and 0 pounds of broccoli, right? So if X is zucchini and Y is broccoli, that is a combination that would actually be fitting for this particular first question. A combination that weighs 10 pounds but doesn't necessarily cost $17. And I can verify that too, because if a zucchini is $1.50 a pound, $10 or 10 pounds of zucchini would cost me $15. So it doesn't cost $17 because I'm not buying broccoli. How about a combination of veggies that cost 17 but does not weigh 10 pounds? Well, if this black line is what represents, and by the way, just for number 1, 10 and 0 is a possibility, but so is 9 and 1, 8 and 2, 7 and 3. Not that one. We'll talk about that in a second. 5 and 5, 4 and 6. Any number that's on this black line that's not this point right here, and again, we'll talk about why in a second, that would be an answer for number 1. Same kind of idea here. This blue line is talking about the cost, right? So combination of veggies that cost $17 but not weigh 10 pounds. So this line, it looks like it ends a little bit after 11. So if you bought 11 pounds of zucchini, 11 pounds of that $16.50. So, that blue line right there represents the broccoli and zucchini that you can buy with $17. Okay, so any point on this blue line is fine. So for example, 4 and 5.5. 4 pounds of zucchini and 5.5 pounds of broccoli. If you're allowed to buy half a pound of broccoli, maybe you are. Okay, so number 1, any value on the black line. And for number 2, any point on blue line. For number 3, how many pounds of zucchini and broccoli can Andre get so that he spends all $17 and gets 10 pounds of veggies? Well, if we have been following along with what systems mean, these two lines have an intersection, a point of intersection. And this point here is the combination of zucchini and broccoli that yields 10 pounds and costs $17. And we can verify that too with the cost. Broccoli is $2 a pound, so 4 pounds of that would be $8. And zucchini is $6 a pound. $1.50 times 6 is $9. So $9 plus $8 indeed does equal $17. So even without the equations, and just in case you're curious, the second equation would be broccoli is y, so 1.5x plus 2y equals 17 would be the second equation that you would use in here. And then, yeah, this is a system that you can solve graphically at this point. And then in algebra later, you'll learn methods that you can use for solving these algebraically. Okay, next question. Which of these systems of equations has a solution of -2, 6? Well, that means that if you plugged in x and y into each system, it has to work for both equations. So if -2 is x and 6 is y, let's see what happens here. So if I look at A, 2 times -2 is -4. -4 plus 10 is 6. So it works in the first equation, so let's give that a check. All right? But if I plug in -2 here, that's -2 times 3 is -6. -6 minus 6 is 12. -12 at that. So it's not 6, it's supposed to be 6, so it doesn't work for the first one. So your way of testing this solution is take these values of x and y and put them into the equation one at a time. It has to work for both in order for it to be an answer. If I look at, say, B, if y is 6 and x is -2, that means 6 minus 2 times -2. 2 times -2 is -4. 6 minus -4 is 10. 10 does not equal 2, so it doesn't work for this one. I don't even have to try the second one, so I know that B is not an answer. If I did x minus y, if I did -2 minus 6, does that equal 9? The answer is no. So process of elimination means that D has to be the answer. X is -2 plus 2 times 6, that's 12. -2 plus 12 is 10, and it does work in the second one as well. So our solution is D. All right, last problem in here. There are 50 athletes signed up for a neighborhood basketball competition. Players can select to play either 6-player games, 3-on-3, or 2-player games that are 1-on-1. All 50 athletes sign up for only one kind of game. Complete the table to show different combinations of games that could be played. So if only one game is going on that has 2 players in it, that means that there are 50 total. 48 players would be left over to play in 6-player games. So if you think about 48 people playing in 6-player games, that means that 7 of those games could, 8 of those games could happen at the same time. Sorry about that. Okay, 8 of those games could happen at the same time, right? Because 6 players in each game, 8 times 6 is 48, and then 2 players in this game, that's 50 players. If only one 6-player game is going on, that leaves 44 players left over to play 2-player games. That means that you would have 22 2-player games going on at that point. That's a lot of basketball courts. If you have 4 2-player games, that's 42 players left over, so that means there would be 7 6-player games going on. 7 times 6 is 42, right? And then if we have 4 6-player game going on, that's going to be 24 players. That means 26 players are left to play 2-player games, which means 13 is going to be the number of games going on there. Okay, so the question here is saying, we have filled the table out here. The question saying if the neighborhood holds, now this table here does ask us to analyze what happens. Well, if we have 13 total games going on and all 50 athletes are participating, how many of those 6-player and 2-player games are actually happening at the same time? Well, if I look and kind of see at the table here, the closest I have out of the ones I have is 7 and 4. So 7 games going on for 6-player games and 4 games going on for 2-player games. Well, that's 11 total games. So we have to kind of look and see what another possibility. What about if I had, like, say, 6 6-player games going on? That would mean that there's 36 players taken up here, and then there are 14 people left to play 2-player games, which means there are 7 of those games going on. So it looks like here 6 and 7 is that magic total of 13 total games and 50 athletes participating. So, and yeah, we could do this with a system as well, but since the table is pretty much already filled out for us, it makes a little more sense to just kind of extend it one more row and kind of reason it out. Okay, so that's the review. I hope you do well on tomorrow's test. I hope that you are going to study and review and ask questions as needed. Have a great rest of your evening.